So this is session 5, where we will be looking at atom economy and percentage yield. These are two types of calculation, and by the end of the session, hopefully you'll be more confident at doing these calculations and you'll understand the difference between the two concepts. Percentage yield and atom economy are both ways of looking at the efficiency of a reaction and the efficiency with which reactants are converted into desired products. But they both look at different aspects. Going back to our cake analogy that we've used previously, here's my balanced equation, if you like, for making cakes. Now, in an ideal world, if I mix all these ingredients together, I should get 12 cakes. But if I do my baking and I add the ingredients and I only get a yield of 10 cakes, then I can calculate a percentage yield. My percentage yield is what I actually get divided by what I should get in theory based on the balanced equation, and I times that by 100. So here I got 10 cakes, I expected 12, times by 100 gives me a yield of 83.3%. So the percentage yield is based on what happens in an experiment under a particular set of reaction conditions, thinking about concentration, temperature, and so on. But we are looking at an actual reaction that we have carried out and done. What was the result of our reaction? The atom economy is based on an analysis of the balanced equation and looking at how efficiently our reactants are converted into our desired product. So thinking of examples with that, in this particular reaction, the atom economy would be 100%. All of our reactants get converted into products. So this time I want to make some meringues, and I need my sugar, I need some eggs, but not the whole egg. I just need the egg whites, which means at the end, once I have my meringues, I've got egg yolk left over. So the atom economy for this reaction would not be at 100% because all these reactants are not just being converted into my desired product, there's other stuff left over. And if we're talking about this in terms of the chemical industry, they're then going to have to pay money to get rid of this leftover product unless they can find some use for it. So in terms of the house, if I ever make meringues, then I tend to just use the eggs to make scrambled egg, an omelette or something like that. But I have to do something with it, otherwise it's just a waste. Bigger issue in industry is if this is something that's harmful to the environment. That's a bigger deal, bigger hassle getting rid of it. So in industry, they're looking for reactions where we've got a high atom economy. That means the majority of our reactants are converted into the desired product. The less waste we have, the less hassle, the less money it's going to cost us to deal with that. So our percentage yield, we are looking at experimental data and we're comparing what we actually get versus what we expected to get, and we're working out a percentage from that. The atom economy we calculate from the balanced equation alone. We don't have to do a reaction. We can look at the balanced equation and figure it out from that. And it's really a measure of how efficient is the reaction at making the desired product without any unwanted leftovers at the end. So we're going to look at two ways to make water and examine the atom economy of both methods. So I can make water by reacting hydrogen with oxygen directly, or another way to make water, one of many, I can burn some methane and I'll make water that way. Straight away, without doing any calculations, I can tell that the first reaction is the most efficient. 100% atom economy. Whenever you see just one product, you have 100% atom economy. All the reactants are being converted into my desired product. So I can tell without doing any calculations that this way isn't as good because I've got two products here. To calculate the actual atom economy for this reaction, I need to look up some gram formula masses to get the relative atomic mass for my reactants. I'm going to total up all the reactants, I need to include the coefficient in the balanced equation, and then I'm going to compare that with my desired product. So again, I'll be looking up my gram formula mass, relative atomic masses to get gram formula mass of water, and I need to take into account the coefficient here. So 16 is my gram formula mass for methane. I have 2 times 32, the gram formula mass for O2, and 2 times 18, the gram formula mass for water. You will have noticed that I'm ignoring carbon dioxide. It's not a desired product. I don't need to do anything with it. So I've gone ahead and totaled this up for the reactants. So I've got the total reactants. Again, remember, take into account this coefficient here. And this side, I've got the total for my desired product. Again, this coefficient is super important. The equation for atom economy is mass of desired products divided by total mass of reactants times 100. This formula, this equation, is at the start of your data booklet. So substituting the numbers in, we end up with our answer of 45% for this reaction compared to 100% for the first reaction. And not only do we have a lower atom economy, we also have carbon dioxide, a greenhouse gas, that we now need to dispose of, which isn't ideal. So let's look at some past paper examples on this. Methanol reacts with compound X in an addition reaction to form methyl tertiary butyl ether, an additive for petrol. And we've got the reaction there. The atom economy for this reaction is 100%. Explain what this means. Why don't you pause the video for a moment and see what you think the answer is, and once you've figured out an answer for yourself, then play the video and see if your answer is correct. So the general idea is that all the reactants are converted into just one product. There are a number of ways of saying that. Here's the marking instructions from the SQA. You could be saying the proportion of the total mass of all the starting materials successfully converted into the desired product is 100%. That's just a wee bit of a mouthful there. Or you could be saying all the atoms in the reactants are converted into the product you want. Or the mass of the product is equal to mass of reactants. There's no byproducts, there's no waste product, only one product is formed. Iron can be produced from iron 3 oxide, and we have our balanced equation there, and they've given us gram formula masses as well. The atom economy for the production of iron is, and you have a selection. Again, I would suggest you pause the video, try this yourself. Do you get the same answer? We're looking for the production of iron. Here it is here. And the thing to pay close attention to while you're trying this yourself is the coefficients in the balanced equation. We must use them. So the reactant side, I've got 2 times 159.6, and we are going to be adding that on to 3 times 12 for our carbon, and comparing that with 4 times 55.8 at the other side. When we work this through and pop the values into our equation, we get an answer of 62.8, which is answer B. Now, hopefully you all got that yourself. Things that can go wrong, you forgot about the coefficients. Or when you were typing things into your calculator, you made a wee mistake or a wee error. Double check you're doing things correctly with your calculator. Another example, we've been asked to find the atom economy for silicon nitride. We are not interested in the other product. When you're looking at this yourself, remember these coefficients. They are really important. So no coefficient there, so it's just 1. But the other two, we've got 3, we've got 16. That means we're doing 16 times everything here. 3 times everything here. Again, as in the last one, they've given us gram formula masses to work with. So If you're having a go of this yourself, pause the video now and come back, play again when you're ready to check your answer. So when we substitute in the numbers, work out the masses, pop them in, we should get 17.9% as our final answer. So a reminder, atom economy, we're working with the balanced equation alone. We've not done any experiments. We're seeing what percentage of the reactants are converted into our desired product using this particular reaction. So we'll look at examples of percentage yield now, and a reminder that this is based on an actual experiment. Whether it's an imaginary experiment that E-Sgoil are telling us about or one we've done in class, we have our balanced equation. We know from our balanced equation what we should make in theory. Then our question is, well, if we actually make this, how efficient was our reaction under these specific conditions, temperature, pressure, concentration, whatever. Aspirin, a common painkiller, can be made by the reaction of salicylic acid with ethanoic anhydride. And they've given us the gram formula masses of the different parts of the equation and labelled the different chemicals as well. In a laboratory preparation of aspirin, 5.02 grams of salicylic acid produced 2.62 grams of aspirin. Calculate the percentage yield of aspirin. There are 4 steps to this question. The first 3 you have been doing since Nat 5. We're going to get the moles of the reactant they've asked us about, which is the salicylic acid. They've told us that there's 5.02 grams of salicylic acid. So we'll calculate the moles of the salicylic acid. Then we will use our balanced equation. Now happily it's 1-to-1 in this equation. We'll then calculate from that the moles of aspirin. Then we calculate the mass of our aspirin. And then we're just going to compare the actual yield with the theoretical yield. So the actual yield they've given us is this. Our theoretical yield is going to come from our calculation from the balanced equation. Now there's always a lot of numbers around in these types of question. I would strongly recommend you're using highlighters to highlight the things you're interested in and score out the ones you're not interested in. So here I've pulled out the relevant information for you. The mole ratio of salicylic acid to aspirin is 1-to-1. We know the gram formula mass of both of them, and we know from the question that we're starting with 5.02 grams of salicylic acid. I'm going to suggest again that you stop the video and you try to do the first 3 steps on your own. This you should be able to do already from Nat 5. So moles of salicylic acid, how many moles of aspirin does that give you? And then what mass of aspirin does that give you? Pause the video now and see if you can have a go at that. So moles of salicylic acid, we should have ended up with 0.036 moles, which gives us 0.036 moles of aspirin. And when we times that by the gram formula mass of aspirin, we should have ended up with 6.55 grams of aspirin. This is our theoretical yield. In theory, with this balanced equation, starting with 5.02 grams of salicylic acid, we should theoretically be able to make 6.55 grams of aspirin. We're now going to compare that to what the question says is actually produced. So our equation for percentage yield is the actual yield divided by the theoretical yield times 100. And we've got to figure out what is our actual and what is our theoretical. We have just calculated our theoretical yield. The actual yield is 2.62 grams. Now we have the numbers as given in the question. To pause again, pop the numbers in the equation and see if you get the same answer. Just play the video again when you're ready. So working that through, we get an answer of 40%. In terms of where the marks are being awarded in this question, The first mark is for calculating the theoretical yield, and the second mark is for calculating the percentage yield. It's a good idea to make a note of these steps and keep in mind that the first three you can do already. They are just your calculations from equations from Nat 5. The last step, percentage yield, the equations in your data booklet, you are comparing the theoretical yield with the actual yield given in the question. So here's our next example, and I would recommend again that you have a go at this now, certainly the first three steps on your own. Calculate the percentage yield of ethanol if 445 grams of ethanol is produced from 1.0 kilograms of glucose. The 1.0 kilograms of glucose is the reactant that you're starting with. Your actual yield is this 445 grams of ethanol. Your job is to find the theoretical yield using your calculations from equations, the first three steps, and then we're going to compare those two numbers. Try and work through yourself to get to the end, then play the video once you're there. Pause the video to do this bit, then play when you're ready to check your answer. Just remember to convert 1.0 kilograms of glucose into grams before you start. So I would pause your video now. So after our first three steps, we should have the mass of ethanol as 511.1 grams. If your answer isn't quite the same, first of all, double check you're working in line with mine. Did you remember to check the balanced equation for the mole ratio? Did you see there was a 2 in front of the ethanol? If you did and it's still not quite the same, it's possibly just down to rounding. Although I have rounded on the page, I didn't round in my calculator. So there might be a slight difference in the answers there. Our final step, step 4, we're going to compare the actual yield with the theoretical yield. Our actual yield was given in the question. We've just calculated our theoretical yield. Time to pause your video, try it yourself, and then play again when you're ready to check your answer. So the final answer should be 87.1%. Again, if you don't have quite the same number, it's possibly a difference in rounding. If your working's the same as mine, you would get the marks. Occasionally they ask the question in a slightly different way. We've got our reaction here, we've got 2-methylpropane reacting to make 2-methyl-2-propanethiol, and they're telling us the yield. A chemist obtained an 84% yield of 2-methyl-2-propanethiol after starting with 30.5 grams of 2-methylpropane. Calculate the mass in grams of 2-methyl-2-propanethiol made by the chemist. So we've got our starting mass of this. We know what the yield is. They want us to calculate the actual mass. It looks quite different, but your first few steps are going to be exactly the same as before. So I'd recommend you start with your highlighter, highlight the things that are related to each, and then start working through steps 1, 2 and 3. So I would pause the video now, try steps 1, 2, 3 on your own, and check your answer to those first 3 steps. You should be able to do that quite easily by now. You've got a mass, you've got a gram formula mass, we need the moles of this, we've got a 1-to-1 ratio, we need the moles of this, and then the mass of this. So pause the video now, play again when you're ready. So working through those steps, we get the moles of 2-methylpropane as 0.54, our mole ratio is 1-to-1, which allows us to calculate the mass of 2-methyl-2-propanethiol as being 49.1 grams. Again, if your working is all correct and you've a slightly different answer, it might just be you've rounded, whereas I've not on my calculator. For the final step, we're still going to use our percentage yield formula, our equation. We're just going to substitute the values in that we have from our calculations and from the question, and that should let us figure out what the actual yield is. So when I go through the workings of this, I'll represent the actual yield as x to begin with, and we'll solve the equation for x. So first stage of substitution, our percentage yield I have from the question, actual yield x, our theoretical yield that we calculated is 49.1 times by 100. So I've divided both sides by 100 to get rid of the 100. And next I'm going to multiply both sides by 49.1 to get rid of the 49.1 in this side. So when we work all that through, we end up with the actual yield, the mass of 2-methyl 2-propanethiol as 41.2 grams. So again, the first steps were exactly the same. The last step, we still used our equation, we just substituted in the numbers we knew already, and we solved for the actual yield. This question was worth 2 marks. The first mark was for calculating the theoretical yield, and your second mark was calculating the actual yield, the mass of the 2-methyl 2-propanethiol. This final example is looking at a question that comes under percentage yield, but it's really more logic than anything else. A 2-step reaction is shown below. We've got step 1, A going to B, and then B reacting to form C in step 2. The first step gave a yield of 60%. The second step, a yield of 90%. The overall yield would be what? Well, percentages are out of 100, so let's imagine we are starting with a mass of 100. It says going from A to B, we've only got a 60% yield. So if I start with 100 and I've only got 60% of that at the end, then by part B, I've got 60. It's now saying we've got 90% of that. So your job then is to say what is 90 over 100 times 60, 90% of 60, and you should find that is 54. Looking at our answers, that means the answer is B. So hopefully you are now able to calculate the atom economy for a reaction, and you're remembering that atom economy is a theoretical look at a reaction, seeing how efficient it is in converting these particular reactants into your desired product. And you could look at that and then pick a different reaction to make that same desired product given a higher atom economy. And this is something that industry uses a lot to try and avoid byproducts that could be environmental contaminants or might just be expensive to get rid of. Of course, they might make a byproduct that has a high value, and so they'll pick a reaction that has a lower atom economy simply because they can make a lot of money from the byproduct. But it's definitely something they have to take into consideration in industry and chemical plants. The percentage yield, we are looking at in reality, how good is this reaction at making this product? Here's my conditions, I carried out this experiment. What yield should I get in theory, and what yield do I actually get, and what is the comparison of those two? If a chemist got a percentage yield that they didn't like, they would then start looking at changing reaction conditions. Can we do this at a higher temperature, a lower temperature? Can we make changes to concentration and pressure? A lot of the time it will involve looking at equilibrium, which is another topic, but using that we can work with our conditions to improve our percentage yield, to make it more economically viable, to make it more profitable for the chemistry plant. Sometimes a lower percentage yield will be acceptable if you're getting a fast rate of reaction and getting a high output rate of the product, but that's something that the companies will have to look at and see what is the most profitable route for them, and that's something that is examined in the topic in equilibria. Percentage yield we calculate from experimental data. What did we actually get versus what did we expect to get? Atom economy calculated from a balanced equation. How efficient is the reaction at making the desired product with no unwanted side products?